Today we're going to work on modeling exponential decay and growth. And we're also going to talk about asymptotes. And that should not be a new term for you, but if it is, we'll make sure you understand what that is. Okay. First of all, what is an exponential function? An exponential function is in the form of y is equal to a b to the x. Where a and b are simply numbers. Okay. A cannot equal 0. And b has to be a number bigger than 0. And one more little side note, b cannot equal 1. If b is equal to 1, we don't have an exponential function. We have a horizontal line where y is equal to a. So whatever a is, that would be our horizontal line. Okay? So b cannot equal 1, and b has to be bigger than 0, but b can be any other number. Okay?
Between 0 and 1?
I'm sorry, what's
So it
that?
can be in between 0 and 1?
Absolutely. In fact, that's where I was headed next. When b is bigger than 0 but less than 1, the function models a decay. Okay? Models a decay. When it's less than 1, when it's less than 1, but bigger than 0, it models a decay. And that graph, sorry, if you weren't done with that, I'll move it back up. That graph is going to look like this. Okay? And this point right here is 0a. Okay? Slide back up a little bit so we can see the model. Let's think about why that point is 0a. That means we put 0 in for which variable? The x. And so y is equal to a times b to the 0. Does it really matter what b was? No, because once I raise it to the 0, I'm going to get 1. Right? I'm going to get 1. And so that means I get y is equal to a, don't I? A times 1 is, no, a times 1 is a. And so if b is 0, then all of this becomes a 1. And so I get a times 1, which is a. And so when x is 0, the y value is a. So my y-intercept is always whatever a is. That's correct. Okay? So the y-intercept is always the value of a. Okay? It doesn't matter if it's a growth or a decay. This is a decay because as my x gets bigger, my y value is decreasing. It's decaying. Things that decay functions model would be like depreciation on your car. All right? And when you buy a new car, the price is way up here, right? And as soon as you drive it off the lot, it drops way down there like that, doesn't it? And it continues to drop in value every year. But it drops less and less and less and less. And it never totally gets to 0, does it? The value of a car is never 0 because you can always take it where? yard, and they'll always give you something for the steel, right? Always. So the value of a car never is zero. Now, if you take really, really good care of your car, then 50 years from now, this function doesn't model that value very well, does it? Because all of a sudden it becomes a what? Louder? A classic. Okay? All of a sudden it becomes a classic, and then that value is going to spike back up. Okay? Probably not way back up to where it was, but it's going to spike back up. Okay? Yeah, actually, you know, if you look back at the 50s, they bought them for $2,000. They're probably worth $100,000 now, some of them. So, yeah, it certainly could go way higher. It's hard to imagine our cars of today doing that. It'll be interesting 100 years from now. I'll be glad to see what happens.
Because they all look somewhat similar. Like
Yeah.
the cars like back then look always pretty.
Yeah, I agree. The different models had their own unique features, where now the three big companies, one puts out a new design and everybody else
No, they look like
streamlines into it.
No, they look like just either shrunk by metal.
Yeah, I agree. But it's hard to imagine that, but you never know. Things happen. Time has a way of changing all this. All right, so anyway, here's our decay model, and that value there is always A. And to be honest, again, my philosophy on graphing is very clear. I know that you can always take your calculator, type it in, and get as accurate of a graph as you want. So all I care is that when you draw a sketch of a graph to me, all I care is that you draw the curve properly. I mean, sometimes people do things like this.
Oh, yes.
Okay, or they do things like, let me draw the axis in here. Sometimes they do things like this, and they're just carelessly circling it back around. Okay? Sometimes they're really careless on where it crosses the axis, if it ever does. Okay, I care about those things. But whether this point right here is exactly right on the graph, or this point right here, or that point right there, I don't care about that. When you draw this graph, make sure it crosses the y-axis at the appropriate place. Make sure the model is correct. If it's a decay, it should fall. And make sure that it's approaching the x-axis, but it's never going to get there, because what was our rule? Okay? So no matter what numbers I plug in for B, and what numbers I plug in for A, as long as I meet these rules here, I will never get it to touch the x-axis. It'll never happen. Okay? It'll never happen. Even if I put 0 in for x, that just helps me find my y-intercept. Okay? If I put a really big negative number in there, that just makes it really small, but it doesn't make it 0. Okay? It can't make it 0. So draw it like this, make sure it crosses here, and that's all I expect of you when you draw your curves. And if you need to find a specific point, you can always type it in your calculator, and you can find that point. Okay? You can trace, if you need to, over to where it's at and find the value. If you need help manipulating your calculator to make it do those things, then I'll be glad to help you. But I think most of you are as good or better at that with your calculator than I am. And so I think you'll be okay there. All right? Is anybody confused on my expectations of what your graph should look like for decay? Okay, let me change the page here, and we'll draw growth. And so in a growth model, it looks something like this. And this point right here is still what? 0A. This is a growth. And in a growth model, the value of B is bigger than 1. So in the growth model, that B value, let me write the model back down so we don't lose track of what we're looking at. This number here, this B value is bigger than 1. So as I raise it to the x power, it's going to get big fast, isn't it? If I pick a number bigger than 1. Say I only pick 2. What's 2 squared? 4. What's 2 to the third power? 8. What's 2 to the fourth power? 16. What's 2 to the fifth power? 32. 6th power? 64. 7th power? 128. Starting to get pretty big, isn't it? And I've only gone to 7. Right? I'm only gone over 1, 2, 3, 4, 5, 6, 7, and I'm up there 128 times whatever A is. Okay? So starting to get big fast. Now, if my B value was 4 or 5 or 6, still, that's really going to shoot up fast, isn't it? 5 squared is 25. 5 to the third power is 125. Now I'm at 3, I'm at 125 times whatever A is. And to the fourth power is 625, and then from there on it really gets big fast, doesn't it? Okay? And so you understand what's happening. This is going to get really big fast. Okay? The bigger the number, then realistically the quicker it's going to do this. Okay? The bigger the B value, the faster it's going to do this. So this would be, B is big.
We'll never do it before the x's.
No. No, because whenever x is 0, that's always this point.
Oh, yeah.
Right? But it can do it right away afterwards. It can come up here kind of slow and then shoot right up in the air. Depending on the values of those, the B and the A. Okay?
So it has to cross the axis.
It has to cross the y-axis at 0A. Whatever A is, that's where it has to cross. Okay? So if I had y is equal to 10 times 2 to the x, then this graph is going to look like this, and this value here has to be 0, 10. So if that's 10, that's 5, and so I went by 5s this time. And so if I do that over here by 5s, okay, I get this. And it's going to get pretty big pretty fast. All right? And your scales don't have to be the same. I didn't have to make these the same. I could have made this 1, 2, 3, 4, 5, 6, 7, 8. I can make my scales however I want. Okay? Sometimes, though, when you make your x and y scales different, sometimes it gives you some strange-looking graphs. In this situation, I don't think it matters. Okay? I really don't think it matters. All right? All right. Any questions on what the growth model looks like? And again, when I grade it, I grade your graph, I'm going to look for 3 things. Okay? Let me write these down. I'm going to look for 3 things. 3 qualities of an exponential graph. Crosses y-axis at A. Oops. Go A, so the next letter is B, right? 2. smooth, appropriate curve. Appropriate, what I mean by appropriate, might want to write down, Garrett. What I mean by appropriate is it's going the right direction. Okay? And the third thing I'm looking for you not to have is, we'll say circling away from the x-axis. So maybe I should say no circling away from the x-axis. All right, I don't want you to turn it into a part of a circle graph where both ends are curling together. Okay, it shouldn't do that. It should be approaching the x-axis because that's called an asymptote. Okay, and it'll get really close to it, but it's never going to touch it. Did I spell circling right? Okay, good. Looks strange. Sorry. We've talked about an asymptote a lot. I think I spelled it correctly, but I'll check. Okay. An asymptote is a line that the graph approaches but will never touch. Okay? It's a graph that the line will approach but never touch. This is a simple one to look at. The fraction 1/2. We're all really good at 1/2. You've already done 2 to the 7th power for me, and you could keep going. I know you can. You can multiply by 2 over and over and over again. I'm very good at that. What's my A value in this model? Well, it's not there, but what's A and B doing in the model?
Is it 1?
Yeah, what are A and B doing in the model?
Multiplying.
Multiplying. So if I'm multiplying 2 numbers and one of them is not there, that number has to be a 1, right? Because if it was a 0, then that would mean none of the numbers were there. Okay? So it's understood to be a 1 here. So A is a 1. And my B value is 1/2. And so if I went to graph this, it's going to cross the y-axis at 1. And it's going to get closer and closer and closer down here. It's never going to touch it. Let's talk about it just for a moment. What's 1/2 squared? 1/4. What's 1/2 cubed? 1/8. What's 1/2 to the 4th power? 1/16. The next one, 1/32. The next one, 1/64. The next one, 1/128. It's getting really, really close, isn't it? If I told you this is your lucky day, I'm going to give you 1/128th of a dollar. You would say, so basically you're giving me nothing, right? You would agree that's nothing when it comes to money.
When you square it every day.
Now if I said I'm going to give you 1/128th of $1 million, you might be a little bit more excited, but 1/28th of a dollar is nothing.
But then if you square
But
it
it's still not 0, is it? Okay?
If you square it every day for a month, it turns into a lot.
No, it isn't, because 1/28 is gonna get smaller and smaller and smaller, yeah. Yeah, if I said today I'm gonna give you a penny,
Yeah.
and every day I'm going to, double it, then yeah, that's gonna get fast. But if I said today I'm gonna give you a penny, and tomorrow I'm gonna give you a penny squared, and the next day a penny cubed, and the next day, what am I giving you every day? A penny. So at the end of the year, you got $3.65.
All right with that.
Yeah. Well, you can buy a cup of coffee with that, maybe. But you understand where I'm going with this? When this number is a fraction, it's going to get really, really close down here, but it's never going to get there.
Is that an option?
Yeah. Okay? So we're going to get really close, but we're never going to get there. So that's what's happening. That's what an asymptote is. It's never going to quite get there, but it's going to get, at some point, we're going to agree it has no value anymore. Okay? But it still isn't zero. Okay? So, we didn't go over any direct examples. Remember, this is a lesson you're supposed to take notes on your own, but since we didn't do that yesterday, I just want to make sure that we have something to get started today so we're not sitting here wasting class time taking notes. So if you need more, you need to look up some more. Do that in your groups, talk things out. When the whole group's confused, raise your hand, I'll come around and help you, okay? Your assignment today was in
It's 3 to 45 by 3.
yep. So you have 16 problems. 3 to 45 by 3, that's 15, and then number 56.
So we can see your test score.
I will wander around and show you your test scores as you're working.
What's your practice?
Let me stop this.